Hello, I am audible. Hello. Yeah. So, how is your preparation going on for GATE? Okay, we will start the class. It's already 7:05. I don't know why the attendance is so low today. Why not well? Adbhut. My screen is visible. Hello, my screen is visible, right? Okay. So, hi everyone. We were discussing GATE 2020 chemistry paper, inorganic chemistry questions from them. So, today we will be discussing first this question number 35, which came in GATE 2020. So the question is, the experimental magnetic moment 3.4 Bohr magneton of a hydrated salt of europium 3 plus at 27 degrees Celsius is significantly different from the calculated value. The difference is due to the given options are a. The population of electrons at higher J levels via thermal excitation. B. Strong ligand field splitting of f orbitals. Option number C. Strong spin orbit coupling. And option number D. Pairing of electrons in f orbitals. Okay. So in this question, excuse me, I am having cold. Okay. So in this question, we have been asked that why europium 3 plus is having 3.4 Bohr magneton as its mu effective value. This is the experimental magnetic moment value for europium 3 plus, whereas the calculated mu effective for this is 0. Now why 0? First of all, can anybody tell me what is the electronic configuration for europium? Anyone? Okay. So europium is basically 4f7 and 6s2. Now, as you in this case, europium is in plus 3 oxidation state, so the electronic configuration is 4f6. Now we know for f orbital 1, 2, 3, 4, 5, 6. There are 7 orbitals, right? So Now there are total 6 electrons. So 1, 2, 3, 4, 5, and 6. Right. So here we are having 6 electrons in f orbital. But as we know that for lanthanides and actinides, it is mostly spin paired, right? So what we consider is in almost like generally in most of the cases for lanthanides and actinides, the electrons are spin paired because of high spin orbit coupling. Okay, coupling constant. So 1, 2, 3, 4, 5, 6, and 7. That means all the electrons will be paired, and therefore, what is the total number of unpaired electrons then in this case? Hi, are you guys there? Because I am not getting any response. Yeah. So actually, if you people are sending me chat, then I can't see it while solving that. So it's better if you people can just unmute yourself and answer. Right. So it is zero. Total number of unpaired electrons in this case is zero. Therefore, the calculated value for this is zero. But in the experimental value is 3.4 Bohr magneton. So now they have asked that what is the reason for this. So mostly in case of lanthanides, what happens is, as we said, that it has high spin orbit coupling constant in most of the cases, and that's why they are paired as well. But there are two examples, like two exceptions in this. One is this europium 3 plus, and the other one is samarium 3 plus. This also I want you people to know. In both these cases, the experimental magnetic moment value is greater than the calculated one. And the reason for this is, like unlike the other lanthanides, in this case, the spin orbit coupling constant value is lower. Okay, it is in the range of about some, it is around 300 centimeter inverse for these two cases, whereas for the other lanthanides and all, it is around 700 to 800 centimeter inverse. Okay, so because of that high spin orbit coupling constant, in other cases it remains as paired and everything stays in one energy state. Okay, in the ground energy state only. But since for europium 3 plus and samarium 3 plus, the spin orbit coupling constant value is low and it is lying almost close to the KT value. Okay, KBT, where KB is the Boltzmann constant. Boltzmann constant, and T is the temperature. Okay, so because of this low spin orbit coupling constant value, which lies almost in the range of kBt, what happens is electrons from the ground state of europium or samarium 3 plus, few of them can like get excited to the upper J level. Okay, so that is why what happens is, let's say for this one actually the ground state is 7F. Okay, for europium 7F0. So what happens is, because of this low spin orbit coupling constant value, the electrons can excited to higher rotational levels, and it can that's why get excited to 7F1 and 7F2 levels as well. So because that means what? Because of the population of electrons at higher J levels via thermal excitation, what is happening is we are getting like unpaired electrons since like in the ground state there are no unpaired electrons, but in the excited like higher rotational levels there are unpaired electrons as well. The reason for getting a non-zero value of magnetic moment is this, like because of the population of electrons at higher J levels via thermal excitation. So the other options are strong ligand pair splitting of F orbitals. So that is like these are kind of general terms for F orbitals. Strong spin orbit coupling, yeah, that is observed for all the other cases. But for samarium and europium 3 plus, the spin orbit coupling constant is not that strong. So this is also not the option. And pairing of electrons in f orbitals, that also happens when spin orbit coupling constant value is very high, and that's why like mostly the mu effective value what we calculate, that is like it will always prefer pairing of electrons because of high spin orbit coupling constant. But in this case, because of less value, electrons are getting excited to higher rotational levels, and because of the presence of electrons in excited levels, we are getting unpaired electrons, which is giving rise to this non-zero magnetic moment of 3.4 Bohr magneton. So the answer for this question is option number A. Is it clear to everyone?
Yes, ma'am.
Yeah. Anyone has any doubt? So you people should remember this time, like they gave an a question with European 3 plus. So similar question can come for samarium 3 plus also. For that, the calculated magnetic moment is around 0.8 for something, but the observed magnetic moment is somewhere like 3, 4, something like that. So for that also, the answer will be same. So keep this thing in mind. These two are exceptional cases for lanthanides. Okay. Then we can move on to our next question. So the next question is from 2020 chemistry paper only, question number 37. So in this question, they are asking that in the following reaction sequence, so here this is the question like how many carbon centers are there? One, 2, 3, 4, 5, 6, 7, right? So there are 7 carbons, so it is each are 7. This is basically a troponium cation. We can see that there is aromaticity here. So this thing is basically 1, 2, 3, 4, 5, 6, 7. Okay. So it is this. Okay. And we have molybdenum center and 3 carbonyl ligands. And we have been asked that what is B. Okay. So here in the reaction, what is happening is NaOMe means there is nucleophilic. It is a nucleophilic addition reaction. Okay, that thing is clear, right? So it is having a troponium cation, and a molybdenum is attached to it with 3 carbonyls. Fine. And we have been asked that what will be the product in 50 degrees Celsius. So first of all, anybody, what is the total number of electron count in this complex? So see, first of all, for this is a question from organometallic chemistry. Whenever you are getting organometallic chemistry questions, you should always start with counting the total number of electron count and all, because we know that 18 electron systems are the most stable one. So we should first check through that logic. Okay. So anybody, what is the total number of electron count for this reactant? Molybdenum is how many electron system? Hello.
Ma'am, it is D5.
Yeah. So this G5 S1, right? So molybdenum is D5 S1. So it 6 electrons from molybdenum, right? 6 electrons from molybdenum. All carbonyls are 2 electron donors, and there are total 3 carbonyl ligands. So 2 into 3 plus eta 7 system. So it is giving 7, and the total charge of this compound is plus 1. That means we will subtract 1 electron. So it is 6 plus 7 minus 1, that is 18 electrons, right? So in this question, what is happening, that in an 18 electron system, in this molybdenum, we are like, there is nucleophilic attack on this molybdenum, like molybdenum complex. So another thing, anybody, what is the oxidation state of molybdenum in this complex? Anyone? Yes.
Zero.
So yeah. So how it is coming? It is because if we consider oxidation state of molybdenum as plus X, then, and we know that carbonyls are neutral ligands, so they give charge of 0, and the stroponium cation has a plus 1 charge, and the overall charge of this complex is plus 1. So X plus 1 is equal to plus 1, or X is equal to 0. That is, molybdenum is a 0 electron, like is in 0 oxidation state. This shows that molybdenum is not electron deficient in this compound, right? This molybdenum center is not that electron deficient in this compound. Here, uh, so actually what happens is, on different temperatures, we get different products. So first of all, um, since it is, if this reaction would have happened at minus 15 degrees Celsius, then this molybdenum center would have, like this OMe minus would have attacked the molybdenum center directly, and we could have got a product like this. Okay. So first of all, here what is the total number of electron count? 6 plus 6 for OMe. OMe carries a charge of, like OMe is a 1 electron donor, and here this is donating how many electrons? We can see that 2 are left there. That means it is donating 4 electrons, right? So 6, 6, 12. It is a 17 electron system. Whereas in this case, molybdenum is 6, this is 4, that is troponium means 7, and this is COOMe is also 1 electron donor. So in this case, it is an 18 electron system, whereas in this case, 6 plus 4 plus 7 plus 1, this is again an 18 electron system, and in this case also it is 6 plus 6 plus 6. Why this is 6? Because here you can see that this whole, all the 7 carbon centers are not attached to this molybdenum center. Okay, this is an open chain, you can say. This is not completely closed. This is open from here. So what is happening is, it is an open chain, and that's why only 1, 2, 3, 4, 5, 6 are donating their electrons. So it is 18 electron system, right? So since here we have to answer that what is B, that means this product is the TCP, that is thermally controlled product. B should be the thermally controlled product. Okay, because at high temperature that product is stable. So 17 electron system is like it is an unstable system and this can't be the product. So like this we can cancel out this option. Okay. Now we know that carbonyl ligands like CO ligands are good for migratory insertion, right? What has happened in these two options? In these two options, what is happening is there are, you can see there is two carbonyl ligands attached to this molybdenum, and in another carbonyl ligand, what happened is migratory insertion happened, and this OMe is getting migrated to one of the carbonyl ligands. So this product is coming like that, and in this the other option C, this option is also not correct because here just one carbonyl ligand is leaving. Okay, so that is not the case. Whenever we have carbonyl ligand, they will prefer migratory insertion rather than like the leaving of one carbonyl group. Okay, so like that we can cancel out the option number C as well. So option number A and option number C are not the answers. Now, what happens is the other remaining options are B and D. So if they have asked you about what is the product A, then this would have been the answer. Like B would have been the answer. But as they are asking for the thermally controlled product, what happens is we know as per Davis Green Mingo rule. Okay, what happens is if the system is or like this is eta 6, right? Eta 6 means this is an even system. Okay, so what happens is in unsaturated ring, sorry, if in unsaturated ring, this even system, if we have, and what I said is this molybdenum was in zero oxidation state. That means it is not that electron deficient. So in thermally controlled product, what will happen is because of the presence of this even unsaturated ring and a positive charge is present there. As I said that this is the tropylium cation. So the attack of OMe minus will be most preferred in the unsaturated ring rather than on the metal center. Okay, so this is since this is the thermally controlled product for this reaction, that's why like the correct answer will be D. Okay, as we have been asked about the TCP, like what will be the product at 50 degrees Celsius. So molybdenum is not that electron deficient center, and in tropylium cation we are having a plus charge there, and it is an even system. So what David Mengo's rule states is that if an like it according to David Mengo's rule, we can compare between different unsaturated systems. Okay, if it is closed, what will happen? Like it will prefer closed system more or an open unsaturated system more, like for polyene system. Uh, and since for even polyene systems, it is like it will be more preferable, and hence the attack is on the diene system, on the polyene system, which is even. Okay, so is was it clear?
Yes, ma'am.
Hello. Any doubts? Is it clear to others as well?
Ma'am, how does the OME attack from the backside? It is showing it is in dash
From the
direction.
backside means? Oh, why OF? Like you are asking about the regional selectivity of this thing. Why it is attacking from the backside?
Yes, ma'am.
So here, like this molybdenum, this thing is present in plus, like sorry, upwards, right? So I think because of steric hindrance only, OME will prefer to attack from the backside of that.
Then there will no be other product form of OME attacking from the. It is coming on the wedge.
See, if there are two options given, then then also this will be the more preferred compound because it is not spherical. It don't have any spherical hindrance. Whereas if it is possible that maybe there will be little bit amount of the other product also present, but if that forms also, that will be of less amount. This will be the most stable one as the whole molybdenum system. This whole system is present on like upwards only. So it will be preferable to for the OMe minus to attack from the backside, from the other side of the metal.
Okay, ma'am.
Okay. And also, like what I said about David Green Mingo rule, do you people know that?
No, ma'am, I don't know about David.
Okay, so actually this Davis Green Mango rule, it is not mango, Davis Green Mingo rule. This is very important for organometallic, like they can ask question like that because like in many places you will get that there are two type of unsaturated systems given and then you have to choose that at which place the nucleophilic attack is taking place. So I would like you people to remember this that nucleophile always preferentially attack at even coordinated polyene than odd coordinated polyene. Okay, so even polyene system is always preferred over odd coordinated polyene. Coordinated polyene. Okay. The second thing is if we have a open system and a closed system, by open system I mean something like this and closed means let's say this benzene ring or cyclopentadienyl ring. Okay, so always open system nucleophilic attack on open system is more preferable than nucleophilic attack on closed system. The third one is if even open polyene is present, the attack is if even open polyene system, then attack on the terminal carbon. Okay, on the terminal carbon. So let's say there is a system eta 4. Okay, open system eta 4. So the attack won't be here or here. The attack will always be on the terminal position, either this or this. Okay, and the third one is that if any electron withdrawing group is present, like for this was for even open polyene system, for odd open polyene system, the attack will be on the attack will be no, it's hanging. The attack will be on the terminal carbon only if an electron withdrawing group is coordinated to the central metal. Okay, so these are the mostly you can say the main rules uh, which falls under this Davis Green Mango rule. So you people should definitely look out in that, and also in organometallics NPTEL videos, you can look into it. You will get more idea about it. Okay, so this is an important rule from both CSIR point and gate point because these type of questions are quite common. Okay, so is it clear to everyone?
Yes, ma'am.
So then moving on to the next question. Question number 13. Okay, from gate 2020, question number 38. So in this question, they have asked the following table lists the reaction or conversion catalyzed by various metal enzymes. So this question is from bioinorganic chemistry. So the given metalloenzymes are coenzyme B12, cytochrome P450, cytochrome C oxidase, and catalase. And here the reactions and conversions are given. So we have to match the correct combination. So for solving this question, you people should know like what do different metalloenzymes do, like what type of reaction or what type of conversion they do. Okay. So for this, I would like to show you first. These are the major types of reactions that are catalyzed by cytochrome P450. Okay. So here we can see that aliphatic hydroxylation, aromatic hydroxylation, like what is happening is from cyclohexane, it is converting to cyclohexanol. That means what? One OH group is getting inserted in these type of reactions. Also in aromatic hydroxylation, benzene is getting converted to phenol. That means insertion of an O, right? Oxygen group. So we can see that the other type of reactions are alkene epoxidation, dealkylation, oxygen dealkylation, oxidative deamination, sulfur oxidation, and reductive dehalogenation. So mostly what I have seen in most of the papers and all for cytochrome P450, they mostly ask about these two things. One is that hydroxylation type of reactions they will give, and they will ask to match the following, like it is asked in this question. And the another reaction which they also ask very often is the epoxidation. Okay, so you should remember these two very well, that they are catalyzed by cytochrome P450. In this option, if we go back to the question, we can see that here in which option oxygen is getting inserted. Anyone? Hi. So in this reaction, what is happening? RH plus O2 plus 2H minus and 2 electron is giving ROH plus H2O. So here we can see that oxygen is getting inserted here from RH to ROH. That means this is that R group. It is not written. It is aliphatic or aromatic, but this is happening, right? Hydroxylation. That means for P is catalyzed by what? Cytochrome P450, right? Then moving on to the next option, which is Q. So here the reaction given is O2 plus 4 electron plus 8 proton is giving 2 molecules of water and 4 H plus. That means what is the reaction? O2 is getting converted to H2O, right? So O2 is getting converted to H2O. So this this reaction is catalyzed by cytochrome C oxidase. Okay, it is a terminal oxidase. The cytochrome C oxidase have two copper centers, and this metalloenzyme is known for catalyzing the reaction from oxygen to water, two molecule of water. Okay, so for Q, it is it is cytochrome C oxidase, right? Cytochrome C oxidase. Now R, in R what is happening? H2O2 means this is hydrogen peroxide, right? So hydrogen peroxide is getting converted to water. Now this type of reaction is done by the enzymes catalases. Here you can see that two molecules of hydrogen peroxide in the presence of catalase generates two molecule of water and one molecule of oxygen. So for R, it is catalase, and in S, what is happening is, so this is an amino acid, right? What is this amino acid? Anyone?
Some glycine.
Yeah. So this is glycine, and it is converted to, this is another amino acid, right? This is CH2OH. That means it is serine. So glycine is getting converted to serine. And these type of reactions are catalyzed by coenzyme B12. So for S, it is option number 1. So where is that option? For what we got is, for P, the answer is 2. For Q, the answer is 3. For R, the answer is 4. And for S, the answer is uh, hanging. So for S, the option is 1. Right. So the correct option among these are, we can say that option number A is the correct option, right? Sorry, no, it's not option number A. For P, it's not A. So for P, it's 2. For Q, it's 3. For R, it's 4. And for S, it's 1. So option number C is the correct option. Fine.
Yes, ma'am.
Okay. So now moving on to the next question. So this is question number 36. So in this question, they are asking the correct combination of ligand L1 and L2 among H minus, NO minus, MECH2 minus, and CO that will satisfy the 18 electron rule for both metal centers in the following neutral molecule is. So in this question, they have given that both the ruthenium centers are following the 18 electron rule. That means they have total number of 18 electrons as their valence electrons. So let's first of all count what is the uh, number of valence electrons for each ruthenium center. So ruthenium is having how many electrons? Anyone?
It's
Hello.
D6 for D6 and S2.
Yeah. So it is giving 8 electrons. Carbonyl gives 2
So
electrons. And this is the cyclopentadienyl ring. So it will give 5 electrons. Plus, we can see that there is a ruthenium-ruthenium bond. So from that bond, one electron will come, right? So it is 8 plus 2, 10 plus 5 plus 1, that is 16 electron for this much, right? Both are having 16 electrons each. Now, the question is, what should be L1 and L2? So as we are saying that this complex is following 18 electron rule, that means both of them should be 2 electron donors. If both of them are 2 electron donors, then only both the two ruthenium centers can be 18 electrons, right? It is clear, right?
Yes, ma'am.
So what are the given ligands? One is H minus, one is NO minus, one is CO, and the other one is MECH2 minus, MECH2 minus. Okay. So what is H minus donates how many electron? Hydride donor? Anyone? So hydrogen is a one electron donor. Okay. H minus is always a one electron donor, whether it is present in bridging position or terminal position. H minus is a one electron donor. Fine. Now the second ligand system given is NO minus. So we know that for nitrosyl ligands, it can either be a three electron donor or an one electron donor. It is a three electron donor when it is present as NO plus and the shape becomes linear at that time. And if it is present as NO minus, the shape is bent. Okay, so here what is given? NO minus. NO minus means it is an one electron donor, right? Now coming to CO, we know carbonyl is a two electron donor, and the other option, that is MECH2 minus. MECH2 minus means one Me is attached to it and one is H. So what is the valency of carbon? We know 4, right? So two are there. That's why this is equivalent to your MECH2 2 minus CH2 2 minus. That means this will donate how many electrons? 2 electrons, right? And we know that for completing the 18 electron for the ruthenium centers, both the ligand system should be 2 electron donors. So among the given 4 options, what are the 2 electron donors? What are the ligands which are 2 electron donors? Carbonyl and the MECH2 minus, right? So therefore, MECH2 minus and carbonyl, this is the correct option. So here both are 1 electron donor, not the answer. Here 2 and 1, not the answer. Here 1, 2, not the answer. In this case, both are 2 electron donors and this is the correct option. Is it clear?
Yes, ma'am.
Okay. So now moving on to the next question. Uh, it is question number 48. Okay. So in this question, among the following, B12H12 2 minus, Ni5CO12 2 minus, C2B9H11 2 minus, rhodium 6 carbonyl 16, osmium 6 carbonyl 20, B5H11, B6H10. The total number of species having nido structure is. So here they are asking that total how many complexes are having nido structure. Okay, wait a second. Okay. So here they have given the atomic numbers also for all of them. So this question we have to solve as per the Wade rule. Okay. So the first option given is B12, H12, 2 minus. So according to Wade's rule, if we are having system like this, BnHn, then BnHn 2 minus means the structure is closo, BnHn 4 minus means it has a nido structure, BnHn 6 minus, that means the structure is arachno. Okay. So for these systems, we can find out like this. Here it is B12, H12, 2 minus. That means Bn, Hn, 2 minus. So what is the structure of this? What will be the structure? Anyone? So here we can see BnHn 2 minus means it is having closer structure. Okay. So this is having closer. Now next we will see for this complex B5H5. B5H11 means what we can do is B5H5 and then how many hydrogens are remaining? 11 minus 5 means 6, right? So here we can write this system as B5H5 6 minus, and B5H5 6 minus means BnHn 6 minus. That means it is an arachno system. The next system is B6H10. B6H10 we can write B6 H6 and then 10 minus 6 means 4 minus. So it is of the form BnHn 4 minus. That means it has nido structure. Okay. Then take this complex. So first we are taking all the main group complexes, okay, which don't have metal. So we saw that this has closo, this one has arachno structure, this has nido structure. Now carbon means carbon has a valency of 4 and carbon is isolobal to one boron and one hydrogen. Okay. So C2 means we can write BH whole 2, then B9, H11, 2 minus. That means B11, H13, 2 minus, or this is B11, H11 4 minus, because 13 minus 11 means 2. So already 2 minus was there, more 2 minus will go. So B11 H11 4 minus. That means it is of the form Bn Hn 4 minus. That means this also has a nido structure. So till now we have got two compounds which have nido structure, right? One is this one is this C2 B9 H11 2 minus, and the other one is B6 H10. Okay. Now next we will see for the metal complexes. So for metal complexes, what happens is first we have to find out the number of skeletal electrons. Now how to find skeletal electrons? Skeletal electrons we can find as per this formula 12 into N minus TVE by 2, where what is N? N is the number of metal centers, TVE means total valence electron. Okay, so by this way we can find out the skeletal number of skeletal electrons in metal complexes, and in this case, as per Wade's rule, if number of skeletal electrons, number of skeletal electrons, which we will denote by n, if that is, okay, let's say this is x, okay. So if this is n plus 1, here this n is the number of metals, okay, you can write as same, where n is number of metals. So if total number of skeletal electrons is 1 plus the total number of metal centers, then it has a closure structure. If it has n plus 2, then it has a nido structure. And if it has n plus 3, it has arachno structure. Okay, so here the given metals are, this one is nickel 5 CO 12 2 minus. So what is the total number of skeletal electron in this? First of all, this is 12 into 5 metal centers, means 12 into 5 minus, what is the total number of valence electron in this case? So nickel has how many electrons? 10, right? 10 into 5 means 50 plus 12 into 2, that is 24 plus 2. So in this case, the total number of valence electrons is 76 divided by 2, that is, did I do anything wrong? 12 into 5, 12 2 12 to 2 is 24 plus nickel is 8 electrons is now. Sorry. So actually this is not 12, this is 10, 10 divided by 2. So it is coming out to be 7. Okay, so 18 into 5 is 90, and then 90 minus 76 by 2, which is equal to 14 by 2, and this is equal to 7. 7 means we have 5 metal centers, so it is having n plus 2 number of skeletal electrons. That means it is having a nido structure, right? And then moving on to the next option, which is rhodium CO, rhodium 6, and then CO 16. What will be for this complex? Rhodium means 9 to 6, 54 plus 32 is equal to 86, 86, and this is 10 into 6, that 8. So, hello, hello, am I audible?
Yes, ma'am. Audible.
Uh, 6 is 54. 56, and so this will have rhodium 6 into 18 and 108 minus 86 divided by 2. So 108. minus 86 divided by 2. It is coming out to be 11. Okay, so this is not n plus 2, right? So this does not have a nido structure. And then the other one is osmium 6 and CO20. So for this one, osmium means again 6 into A is 108 minus osmium for is iron, putting in osmium. So 8 into 6, that is 48 plus 40 is equal to 88 divided by 2, 8 minus 8 divided by 2, which is equal to 10. So this is again not equal to n plus 2. So this is also not Nido. So among the given options, we can see that only 3 had Nido structure. One was this C2B9H11 whole 2 minus. One is nickel 5 CO12 2 minus. This has a Nido structure. And the other one is B6H10. This also has a nido structure. Therefore, the total number of species having nido structure is 3. Okay, so this will be the correct answer. Is it clear?
Yes, ma'am.
Okay. So, any questions from this class? Okay. So again, if you people have any doubts, you can mail me at. Okay. So okay. This was Gunasuli. So you have written the correct formula is TBE minus 12n by 2. Okay, wait. Okay, so yeah, this should be the TBE minus 12n by 2. Six minus 12 is the 60. So here you are saying for this which system Gunasili 86 minus 72 by 2. Uh, hello, hello. minus, and for nickel then for the case of nickel it is 5 into 10 electrons plus 24 plus 2, 76 minus 60 divided by 2. Then for nickel 5CO12 whole 2 minus, the total number of valence electron will be, okay, so it is then not coming out to be that. Okay, so I will just do it and get back to you in this question, for this question. Okay, the correct formula for this. Is it fine? Hello. Okay. Okay. Sure. Thank you.